Although Hyperlambda is a very easily understood programming language, it actually contains quite strong support for multi-threaded programming. So in this session, we're going to look at some of these multi-threading features of Hyperlambda. And the way we're going to be doing that is by using HTTP GET, which are a slow invocation that requires a lot of time. Then we're going to fork out these HTTP GET invocations into multiple threads, and then we're going to look at how to join our threads later. Now, if you have your cloudlet up running, then click MISC, go to the evaluator, and let's get some space here, and let's do http.get : 2 double quotes https : aista.com. If we now execute this, you will see it takes some time. Why? Well, because our backend cloudlet actually needs to fetch the HTTP invocation that we're passing in as the URL. And this is a lengthy and a costly job. And of course, the amount of time grows linearly according to how many HTTP GET invocations we have. So if we add a couple of more HTTP GET invocations, like this, and we're executing 4 of these guys, then if you look at the time it takes to actually return our Hyperlambda, it grows and grows for every single URL we add to this. What we want to do for such operations where we are waiting for for our network card to actually return data from some external source is that we want to create forks. If we add in front of all of these guys, we add fork, tab, then we add fork, tab, then we add fork, tab, then we add fork, tab. Then all of a sudden the invocation returns immediately. However, at this point, we're actually not getting any result. This is because what we just created, we created now 4 fire and forget threads. If we want to wait for these threads to actually return data before we proceed to line 13 here, then we need to add a join statement at the top, and then we need to make sure that all of our fork invocations are inside of that join statement. If we now execute the code, you will see that it executes, it still takes a little bit of time, but it actually executes much faster than when we only invoke the HTTP GET invocations sequentially. Why is that? Well, because actually what is happening here now is that it's retrieving these HTTP GET invocations in parallel. So what is happening here now is that the Hyperlambda runtime creates 4 threads. Then on each of these threads, it in parallel retrieves the HTTP GET invocations here from the URLs we provide to it. And then when it comes down here at the bottom, it will wait for all of our threads due to the join keyword to join before it proceeds. Now I want you to save this snippet, and actually let's write a comment above and explain what the snippet does. And it creates 4 threads and waits for all threads to return before it proceeds. Then we want to save this snippet for later references as tutorial-05-01 and click save. Now let's measure the difference between these 3 different ways of invoking an HTTP GET invocation. First, let's copy this piece of code and let's paste it in such that we have 3 versions of it. Now the first version, we just want to remove our join invocation. And then we want to write as a comment, creates 4 fire and forget threads. Then in the second one, we want to keep the join. However, in the third one, we want to completely remove the fork invocations here, such that we are actually sequentially invoking 4 HTTP GET invocations here. Now creates for sequentially invoked HTTP GET invocations. Then we can save our snippet again as tutorial 0501. Now, so this is obviously the fastest one. However, before we start measuring, let me tell you about a feature that the Hyperlambda evaluator have. You see, if I now select this text and I click F5, then the Hyperlambda evaluator is only going to execute my selected code. However, before we do that, click F12 to show your browser developer tools. And then select the top code here at the top that only has the forks. These are our fire and forget threads. And as we can see, it returns in 105 milliseconds. It's fairly fast. If we now select this second code snippet that actually executes each of our HTTP invocations in parallel for them to join all of our threads and wait for all of our threads, we will see that it takes 921 milliseconds to execute. If we go down here and we execute all of our HTTP invocations in parallel, we will see that now it takes 1.19 seconds, right? This is because of what is happening here is that here it's creating fire and forget threads and it returns immediately because it never waits for the result of the thread. At our second example, it creates 4 threads, it executes all threads in parallel, but it waits for all of the threads to finish. Since all of the threads are being executed in parallel, this means that all HTTP invocations are executed at the same time. If we go down here to our final example, this executes our HTTP GET invocations sequentially, meaning it first invokes this, then it invokes this, then only when this is done, it invokes this, when this is done, it invokes this, and so on. So this allows us to do multiple tasks at the same time, not having to wait for our tasks to sequentially execute before the next part of our task is being executed. Hyperlambda has a lot of different thread helper slots, some of which are encapsulated in the join and the fork keywords, and other helper thread slots that we will look at now. Sometimes you need to do what is commonly referred to as thread synchronization. Now, in order to demonstrate that, we can first delete all of this code, and then let's create a Lambda object, .lambda, and then type tab, and then let's do io.file.load, colon, slash, foo.txt. Now, let's save this snippet as tutorial 0502. And let's go to Hyper IDE and let's create a file. Let's call it foo.txt, active folder, new file, foo.txt, create. Then let's just add some code to it. This file will be dynamically concatenated to by multiple threads. Character return, save the file. Let's go back to our evaluator now and let's load our tutorial 0502. So this thing here now loads the file. Now we can append to the file strings.concat get-value :x at io.file.load appended by lambda object 1 \r\n. This is the standard string way of applying a character return and a new line into a string. Now, if we call this lambda 1, then we can create another lambda object below. But before we do that, we want to do io.file.save colon slash foo.txt. Now we want to pass in as the content of the file get-value :x at strings.concat. What we're basically doing here, we're loading the file, then we are concatenating this string into the file, and then we are saving the file again. If we now simply invoke eval colon x colon at dot lambda 1 and we execute this file, then let's save the snippet first as tutorial 0502, and let's go back to HyperID and let's look at our file. You see now we dynamically appended a piece of text into our file. So now let's go back to the evaluator, load our Alt-L, by the way, to load things. Every single keyboard shortcut that exists in Magic, you can see here. So wherever you are, if you click the short keys button in the top right corner, you can actually see the shortcut that exists. Now let's create another Lambda object. And actually, let's just copy this guy for simplicity reasons. And let's call this one Lambda 2. Now we can execute these sequentially like this. And if we now save our snippet first, and then we execute our code. If we now go back to HyperID, let's open it in a different browser window and we see our file. We see, well, we should probably change the text here and do appended by lambda object 2, save our file, and then execute the file. If you now close the file and reopens it again, you will see we have appended by lambda object 2, by lambda object 1, etc., etc. If we now want to do this in 2 different threads, we are left with a problem. And actually, before we illustrate that problem, let's move this guy up here, such that our code looks like this. And let's create a thread, fork. And then let's just select this code, click tab, and then let's do the same here, fork. And let's select this code and just click tab here. Thread number 1 loads a file, concatenates to it, and saves the file again. Let's write the same comment down here, except we'll change it to thread number 2, and then let's save the file. We now have a problem. Why? Because we now have 2 parallel processes accessing the same shared resource at the same time. What we need to do, we need to now apply something that's called thread synchronization. And we only need to do this when we are saving the file. Actually, we need to do it when we are loading the file too, because otherwise we might have one of our threads loading the file, then editing the file and saving it, and with maximum bad luck, the other thread would have loaded the file before the file was saved, implying it will not be given the changes that thread number 1 actually added to our file. So what we now want to do, we want to use a semaphore. Semaphore are names, semaphores are named. So we can call our semaphore thread. That's a nice name. Then we want to indent the code here. Then we want to have the same semaphore down here. And then we want to indent all the file manipulation parts of our code, the parts of our code that actually accesses our shared resource, such that it becomes a Lambda object to our semaphore. If we now save this snippet again, and we execute it, F5, and we go back to HyperID and we close this guy and we open it, you will see here now that it is actually correctly appending strings to our object. If we delete all of these guys, we save the file, we go back here, we execute this 3 times, we close the file, we reopen it again, you see lambda object 1, 2, 1, 2, 1, 2. Now I want to emphasize the order here is not necessarily thread 1 and thread 2. The order here is actually undetermined. However, the point of the exercise is that as long as one of our threads has the semaphore and owns the semaphore, no other thread can exit the Lambda object inside of our semaphore invocation. And this ensures that we have thread synchronized access to the code that consumes our shared resource. So let's save this snippet for later, such that we have the whole code and we can return back to it if we want to return back to it for reference purposes in the future.